An especially important application of induction in computer science is proving that an algorithm is correct, that it does what it's supposed to do, always for every valid input in some set of inputs. So here, what I want to do is I want to give our first example of a proof of algorithmic correctness using induction. To do this, we need to make a few definitions of familiar ideas that we need to formalize and state in a kind of systematic way. So here's our first definition. A string is a sequence of symbols from some set S, which we often call an alphabet in this context. So here, a string S is a sequence of symbols, S1, S2, S3, S4, all the way down to S minus 1 and Sn minus 1 and Sn, where each of these individual characters are taken from the alphabet. Here's a few examples of strings. So here, the alphabet is the characters A, B, and C, and some strings from this alphabet are A, B, C, A, B, B, A, ABBA, and C, A, B, B, A, B, kebab. There's a special string that we often call epsilon. This string contains no symbols at all. The string contains no symbols at all. It's a little bit like an empty set. It's just an empty string. Finally, for our definitions, there's a reverse operation on a string. So if S is a string with a sequence of symbols S1, S2, S3, S4, Sn minus 1, Sn, the reverse is just the same set of symbols in the opposite order. So we call this S hat. S hat is equal to S sub n, Sn minus 1, all the way down to S4, S3, S2, S1. An important point here is that the empty string is considered to be its own reverse. Epsilon is equal to epsilon hat. Okay, so now we have the idea of strings, and we have some definitions to go with them, particularly the reverse of a string. We just take all the characters and we swap them in their order. Now, here's a question. How do we compute the reversal of a string? How do we make that happen? How do we compute the reversal of a string? Here's an algorithm for doing it. So I've written this algorithm in some Python-like pseudocode. So here we are. I'm going to call my algorithm reverse. It has one argument s. And here's what we do. If it's the case that s is the empty string, we're just going to return the empty string. Otherwise, if s is not the empty string, what we're going to do is we are going to return s minus 1, so that's the last character of s, and then we are going to call reverse on the remainder of s. So that's all of s except the last character. So what's going to happen here, we're going to take the last character of s, and then we're going to put that at the front, and then we're going to call reverse again on what's left of s, everything except the final character. And here, you might notice this is a recursive algorithm. This is a recursive algorithm for computing the reverse of s. It's recursive because it's an algorithm reverse that calls itself. This is our base case, and this is our recursive case. If the phrase base case sounds familiar from induction, it really is. An awful lot of the structure of induction is extremely parallel to the structure of recursive algorithms. So, theorem, mathematical fact, guarantee, count on it. This algorithm works. And what do I mean by works? I mean that the reverse of a string s, as calculated by this algorithm, is guaranteed to be the definition of the reverse of the string s. So reverse, the function always correctly calculates reverse the mathematical object for a string s of any length n greater than or equal to 0. Often, when we are doing proofs of the correctness of recursive programs like this, we need to say, okay, this is going to work for any input. of any length, and you'll notice that the length here, n greater than or equal to 0, that kind of has the vibes of something that we could use for induction. So indeed, n is going to be the variable of induction in this case. So let's go ahead and prove this theorem. So our proof is indeed going to be by induction. So for our base case, we need to consider the case n equals 0. Now, what's the only zero length string? The only zero length string is s is equal to epsilon, the empty string. In this case, the first branch of the if statement executes. So the first branch is right here. We check if s is equal to epsilon, the empty string. Answer, yes, it is. And we therefore return epsilon. So in this case, the reverse of epsilon is epsilon itself. But we know that by definition or convention, depending on how you want to look at it, epsilon is its own reverse. Epsilon is equal to epsilon hat. And that's what we needed to show. We needed to show that reverse returned the reverse of the input string. Here it has done that in the base case. So we're done. Boom, base case established. Okay, now we need the inductive step. So for the inductive step, what we do is we assume this algorithm works for any string of length k. So suppose that, and remember what it means to say that the algorithm works is that reverse of s is equal to s hat. Suppose that this is true for any s of length k, where k is greater than or equal to 0. Now, I'm going to define a string t. Let t be a string of length k plus 1. Then I'm going to consider t to have two pieces. So the first piece of t is t from its first index over to its kth index. And then there's the final character as well. So t is in two pieces. It's the last character, and then it's everything before the last character. And in particular, everything before the last character, t1 through k, is a string of length k. Okay, so this sounds good already because I know things about strings of length k. I know that the algorithm works on strings of length k. So I know that if I do reverse of t from indices 1 to k, that result will be t1 to k hat. That's my insight. Now I'm ready to figure out what reverse of t itself is. So let's do a calculation. Let's check. Reverse of t is equal to, and now here we need to check. I know that t, if t is a string of length k plus 1, it's not a string of length 0. It's not the empty string. And so that means I'm going to be executing this second clause in my if statement, the else clause. So that means that the reverse of t is going to be the very last character of t concatenated with reverse of t 1 to k, which is equal to the very last character of t followed by the reverse of the first k characters of t, which, if I write that out, well, the very last character of t is also tk plus 1, and then the reverse of t1 to k is just tk, tk minus 1, all the way down to t2 and t1. And guess what? That very last expression here, that's the reverse of t. So we did it. This means that since t was arbitrary, we've proven that the reverse algorithm works on any string of length k plus 1. That's what we wanted to show, and therefore our inductive proof is complete. So with this tool of induction, we can look at algorithms, and actually, if our algorithm is correct, we can often prove mathematically, beyond a shadow of all doubt, that the algorithm that we are studying correctly achieves the task that it says it does.